mathematics attracts a lot of obsessive people who are obsessed with solving puzzles.
I don't know if mathematics attracts obsessive people. Yes, obsessed with solving problems. I think there's a certain amount of focus that's required. And I think brains work in different ways. And I think being able to achieve that focus for longer periods of time is almost necessary. And sometimes obsessiveness results. I mean, so obsessiveness is bad as well, right? If you focus to the exclusion of everything else. But the need to be able to focus for a certain period of time is necessary. And you get very elegant answers out if you do that sometimes. Okay, so I'm going to go on with bifurcations today, and then I'm going to do a little bit of chalk and talk, depending on what rate I finish. In particular, I would look at the Duffing oscillator, because it gives a good example of how frequency dependence on amplitude actually arises naturally. Okay, so what we've been doing is looking at bifurcations. Okay, so basically the parameter dependence of solutions. We saw that all the bifurcations we had in 1D generalized to 2D. They, in sort of like the saddle node bifurcation, all the bifurcations with fixed points generalize. And then we started looking at bifurcations that oscillatory, that actually go from a fixed point to a spiral. Okay, and we're going to look at a number of those today, and then give quite an interesting example where you once again get hysteresis as well, but this time with just one parameter. So we had the supercritical case, which I just need, actually I didn't want to start here. Sorry. Yeah, so we were there. We had the supercritical case of the Hopf bifurcation. And what we saw was it was this normal form where you had AR in the radial coordinate minus R cubic. So this minus R cubic always stabilized the problem. In other words, there was always a point that if the radius got large enough, R would decrease and it would come back to somewhere near zero. And so what we had here is we had the stable fixed point over there. When you got to zero, the fixed point at zero became unstable, and you went onto a branch which corresponded to a non-zero radius for a limit cycle, and it got bigger and bigger as time went on, but you would always be attracted to a limit cycle. Okay, and so this is the bifurcation diagram for the radius, or the amplitude of the oscillation. And here is actually the full bifurcation diagram where you had stable spirals for A negative, the bifurcation, the very weakly stable spiral that was basically dependent on the minus R cubic term for A equals to 0. And after that, your solutions approached an oscillation, which was a limit cycle, which went round and round like this, and it got bigger as time went on. So in some sense, it was a very, very safe solution. So if you were in the tutorial yesterday, you would have seen actual critical or sort of examples of how this occurs. The flutter, where you sort of had the plane was stable, and then as the oscillation, as the speed increased, then the thing started oscillating with a certain frequency. That was an example of this type of bifurcation. So just as when we were looking at the pitchfork bifurcation, we also had a supercritical and a subcritical case. And I said the subcritical case is dangerous. So in a Hopf bifurcation, you also have a supercritical, which is the one we've looked at, which is basically just a 1D pitchfork bifurcation in radius, in amplitude. And we also have the corresponding subcritical case in a Hopf bifurcation, which is really, really dangerous. And I'll tell you why it is really, really dangerous now. Okay, so we're now going to look at the subcritical Hopf bifurcation. And what it is you start with an unstable limit cycle, okay, that surrounds a stable spiral. So let's just draw it. So for some parameter range, in this case it's going to be A, the same as the last one, you start with a stable spiral in the middle, And then around it, you have an unstable limit cycle. And then what happens is around the unstable, because the limit cycle is unstable, around that, you have an unstable spiral. So the solution, as long as you're not inside this purple region, or the pink region over here, is going to run away to infinity. There's only a very small region that actually attracts it to 0. And what happens with a supercritical Hopf bifurcation is that thing then goes and it changes the limit, the unstable limit cycle. So this dotted black line shrinks, okay, to a point. So it gets smaller and smaller. So the region around this stable spiral gets smaller and smaller. The region in which you can have a stable spiral gets smaller and smaller. And so you basically have the situation. Your stable spiral is now shrunk. Your unstable limit cycle is over there. And the region that runs away to infinity is over there. And then finally that thing disappears, the black limit cycle disappears, and you're left with only an unstable spiral, okay? And typically this unstable spiral runs away to infinity really, really quickly. So, and engineering-wise, this is a dangerous situation to be in. So, very often, it turns out, it's easy to build something that is stable in a small regime and then runs away catastrophically. This is why the people are too scared to change the Boeing design, because they're scared they're in this region where they have they've designed the thing in the shape that it's a reasonably stable aircraft, and it's got a large region of stability. They've been flying Boeings a long time, and they're reasonably stable. They're scared that if they make a dramatic change on the design, they actually shrink that region where it is stable and they result in more accidents that with the amount of people flying now will leave them bankrupt or liable for generations. So the aircraft design has not changed except for the fighter planes, and recently where people have been starting to play with drones. Okay, so we saw some of what could happen if you had an instability in an aircraft, and it was one of the big problems initially with aircraft design, and still is on occasion. And that we discussed in the tutorial, and I hopefully can get that video up at some point as well. So if you haven't seen it, it's well worthwhile at least going through it. So the classical example, or in some sense the normal form, is once again just as r dot equals to ar minus r cubic, and just as the pitchfork bifurcation, we now have this plus. And you can see it's this plus, which in front of this r cubic, which is the destabilizing term. It's basically the term that says for large r, this solution is always going to run away to infinity, and it's going to do it quickly, really, really quickly. Okay, and then omega dot is one against the frequency that has a very base frequency, and that basically indicates that everything is going around anti-clockwise over here, and it also has this BR squared term that I might say a bit more when I look at the Duffing oscillator I wanted to look at. Okay, but anyway, what this thing means is that the frequency gets larger as you go away from the origin. So the larger R becomes, the more rapidly this thing is going to rotate. Okay, so that's just the subcritical prick form in the amplitude, and this is the oscillation frequency. So it's very, very similar to the supercritical case we looked at the last time, except that it has this property that it always runs away to infinity for large enough R. And so let's analyze it carefully. Once again, we're going to use the one-dimensional analysis. So there's a fixed point whenever this thing, in radius, whenever this thing is 0. In other words, that happens when R is equals to 0 and when R equals to plus minus the square root of A. Okay, so the fixed point, we can once again at R equals 0, you can do the 1D analysis. If A is greater than less than 0, you can show it's a stable fixed point because the derivative is negative. If A is greater than 0, it's an unstable fixed point. And if A equals to 0, it's where the Hopf bifurcation occurs. So the A over here is actually the A I used to draw these things. So here you can see for just the fixed point, so at R equals to 0, A less than 0, it is stable, so it spirals in, right? Because it's a spiral, the r is just the radius. It always decreases to 0, but it's continuously spiraling because your theta is positive. Here, as a increases from a negative thing, this region gets smaller and smaller, but it is still stable. Eventually, when a equals to 0, it is marginally stable, and in fact, weakly unstable because of the odd with the or cubic term that runs away. If a is greater than 0, it's an unstable spiral. So you just see the nature of the fixed point being reflected in these diagrams already. The second fixed point thing arises if a is less than 0. Okay, then r dot is 0 when r equals to the square root of minus a. So in order for this root to exist, you need this condition. So it only exists if a is less than 0. And that corresponds to a trajectory where the radius doesn't change, and it's a circular limit cycle. And you can actually see this thing depicted over here. So there a is negative. Here is our circular limit cycle. So you can see the heuristic example I gave is in fact exactly this normal form that we've worked out. So there's our limit cycle. As a gets closer to 0, right, it shrinks because the square root of minus a gets smaller. And then finally, when a is greater than 0, it completely disappears. And so when I analyze these things, we want to once again draw the bifurcation diagram. And we'll first draw the bifurcation diagram in just the radius, because that's basically the important thing that determines the dynamics. And then I'll say something about what happens with these as a result of the bifurcation diagram. So the first thing is, let's put everything on a plot. We put our fixed point. If a is negative, it's a stable fixed point, so it's over here. If a is positive, the point at r equals to 0 becomes unstable. So there we have it. The second thing is we want to put in this fixed point. Okay, so if a is negative, r equals to minus the square root of a. So basically you have that, another way of plotting it is just simply to say a is equals to minus r squared, and so we have it over here. Okay, so there is our second fixed point. We know that it is unstable, and we know that by either simply looking at our diagram that we plotted, or by looking at this thing, taking its derivative and seeing that it's positive over there. Or another way of doing it is just pick a point over here for a given r and a and work out the arrows of what r does, right? So all those are fine ways of doing it. And so what happens is anything that you design in this way is going to have a stable fixed point, and then if you get into certain parameter range, it spectacularly disappears. Okay, and violently disappears. And the region that separates the thing that gets attracted to the stable fixed point is basically this dotted line. Okay, and the point at which the fixed point changes is called the bifurcation point. Okay, and that's at a equals to 0. So, and this is the Hopf bifurcation. And so what happens now, if you put in the arrows, everything in here goes down to the stable fixed point. Everything above the thing runs away to infinity, which is basically just these drawings shown again, except just now with respect to looking at the radius only. And then over here, where a is positive, it also runs away for everything. Everything is unstable. And so your basin of attraction for the stable fixed point is this very small region under the parabola. Okay. So only that thing is stable. And the problem with these systems is that when the fixed point loses stability, it runs away very quickly. Okay? And the trajectories jump. And typically, they've got to jump to somewhere. So the most vicious is they just jump to infinity and you have an explosion. Other things are possible if you can have a distant attractor that's far away, that we'll see when we start doing chaos, it can go to that. That's a good outcome. If there's a fixed point, so any attractor, if you have a stable fixed point somewhere, it's most probably going to run away to there. Or if you have a limit cycle, a bigger one, it can also run away. That's stable. That can also run away to there. Or, in fact, you can have a strange attractor. So the basic thing is just these equations we've given here are going to run away to infinity. But if you have a more complicated system, it's usually going to run away to something else. And the problem is if you're engineering a system, you've got to design it in a way that it runs away to something else that you know. Okay? The most classical example is nuclear reactors, right? So you have a nuclear reactor. All nuclear reactors should be designed so that they have the supercritical case. In some sense, you have it off, and then when you switch it on, it slowly increases on. Or you have it in a state, you change it, and you can slowly increase the power. If something happens, you make it that it crashes back and it switches off. That's how you design it. So you want an infinitely large region of stability for your nuclear reactor. You, under no circumstances, want any chance that its energy output is going to run away to infinity. Now, it turns out it's not the only way to design a nuclear reactor. The most famous nuclear reactor, if you put a nuclear reactor in a situation where you have a tremendous amount of neutrons, slow neutrons together, it can explode, and it can explode violently. And there is a design of a nuclear reactor that doesn't that is subcritical. And the famous example is the Chernobyl reactor. I don't know if you know what that was. Okay, it's a reactor in Russia. It was a subcritical reactor. It was basically had a region in it which it was stable. And instead of being a reactor where you sort of like push it on all the time, you had to physically push it down or damp it down. In other words, it continuously wanted to explode and you stopped the explosion. And it turned out that region where you could stop the explosion, if you tweaked it a little bit, it would just explode. And people are brave. I mean, you push the envelope, and the reason why it was designed that way is it's cheaper. It's easier to do, right? Because uranium, if it has a certain conditions, it wants to explode. And if you don't, it's very expensive to actually design a reactor where you've got full control. So anyway, Chernobyl was a subcritical reactor. And what they did is they had basically, you have the uranium, it gives off neutrons. You slow the neutrons down because the neutrons it gives off is fast. You let the neutrons knock around water, heavy water or something else, or something like that, gives away its kinetic energy. It's a slow neutron, and a slow neutron can then knock out several more neutrons from the uranium. And then in order to stop the thing from exploding, you put something in there that sucks out the neutrons, and then it doesn't put out so much energy and your chain reaction slows down. And so what happened in Chernobyl's reactor, there you basically had this core, you had your neutrons, and you had rods that you push in, and it actually then absorbs the neutrons and the energy decreases. So on one unfortunate day, the rods got stuck, and they couldn't stop the reactor, and the thing went, the stable fixed point that they had, which was giving out a set energy which wasn't at zero, went past this point, and the thing exploded, killed lots of people, poisoned the area for generations. So don't design things that have supercritical Hopf bifurcations. I mean, another example, once again, if you have a Hopf bifurcation where the zero amplitude, say you start from not a fixed point, but something that has a non-zero amplitude, say a limit cycle, it's your heart rhythm, right? Your heart rhythm is a limit cycle. It's got a region of environment that it is stable, right? You can go for exercise, you can put the heart rhythm up, it will come back eventually to its rest state once you stop the exercise. So there's a tremendously large dynamic range for a healthy heart. What happens if you have like cholesterol or something, that part of the blood vessels in your heart dies? Or in fact COVID, like my brother got COVID and his heart got affected. So his stable region is now smaller. Okay, so if he exercises, then he gets a very, very rapid heart rate that his body basically starts shutting down, and he can't, which is difficult for him. Anyway, so that region where this heart rhythm is stable becomes smaller if you damage your heart. So there's less range where you can actually push it and exercise it and actually still have a healthy rhythm before it goes into this jelly state where it doesn't pump any blood at all. Fortunately, the human body is amazing, and in his case, right, it's self-limiting. His body tells him he can't run faster because his heart muscle is damaged. Whereas sometimes when you have a heart attack, you don't always know, and that happens with a heart attack. If something suddenly dies, like my mom, it does seem like my family's got a lot of heart problems at the moment. Anyway, my mom actually had a heart, and she's older, so the one blood vessel that supplies the one cavity in the heart, that died. Yeah. So that died. It was no longer supplying her with blood. She happened to go to the doctor for another reason. And he said, there's something wrong with your heart. And she says, no, I feel fine. I don't know it at all. He says, no, there's something wrong with your heart. And he says, you must go, and he checked her in, and he says, maybe you can do where they put a little pipe in and open the vein again. And they had a sonar done, and basically imaged the heart, and they saw that the blood vessel was completely dead, right? And the guy, when they were going to put it in, the guy says, there's no way I can operate, and there's no way you're leaving the hospital. You need to go into the hospital straight away. And he says, you are very, very blessed to be alive. Because what had happened in her case, you've got two veins that supply the two ventricles. And what had happened in her case, her one vein had actually got these fine veins, and it had grown around. And the second one was supplying the heart muscle, so the heart muscle hadn't actually died. So they could save that, right? They put in a vein, they took it out somewhere else in the body, and actually grafted it on that the blood could flow directly. So it was an amazing miracle that she wasn't dead, actually. But anyway, whenever you change that heart muscle, you change the stability region where it is stable. Okay, and then you run the risk of running over something like that catastrophically no longer can beat and can no longer sustain a limit cycle. Okay, so very dangerous bifurcation. You must start getting heart palpitations, actually not very serious ones, if you ever come across a supercritical Hopf bifurcation in design. Okay, and the way you recognize it, it's basically got some parameter A, but the dangerous term is this cubic explosive term, because that's the thing that drives it unstable. Okay. Right, so what I now want to do is, in practice, you don't usually end with a cubic term. In practice, once you have this fixed point that goes unstable, it's going to jump to something else if you've designed it well. And so I just want to give you an example of that, which is once again coming back from some of the examples we did in the one-dimensional case, just with limit cycles. But in practice, it's going to go, you're going to get to this point, and it's basically like jumping off a cliff for your solution, right? You're at the fixed point, you get here, and suddenly your fixed point is gone, and it's going to run away to something else. So I just want to show you an example of how that happens. And not all these things are bad. This type of bifurcation you get in transistors. You get it in superconductors. And you get it in many chaotic systems. You get it in the weather, where you suddenly have this jump from where you have a stable state, it goes to somewhere else. You get it in economics as well. And so I don't want to leave you with the idea that it's completely catastrophic, but just be very wary when you start getting it in engineering, and be sure that you understand the system enough that you are left with that term only. If you get a term like that, you have to do more work to try and get the thing stable. So let's look at it. Okay, so all I've done now is I've still got this radius, equation for the radius. I'm still writing in polar coordinates. I've got this term that gave the supercritical Hopf bifurcation over here, and I've added this minus r to the 5 term. So this thing, because it's negative at large r, it stabilizes it, right? You always, if r gets big enough, your thing is going to shrink. You're not going to explode. And once again, I'm just going to leave the thing that the angular equation that makes it keep going round, I'm going to leave that here. Actually, as an exercise, maybe you should take this equation, write it back in xy coordinates. Because you can do it the same way you went from xy to polar coordinates, you can write it back in xy coordinates and just see what it looks like. And then you'll see why we are analyzing it in polar coordinates. So what happens now is, once again, we have the fixed point at r equals to 0, because you can factor the r equals to 0 out. And so let's put it, this is basically how I solve it. Whenever I get something, I put it on the plot. So let's put our fixed point in there. If r equals to 0 and a is negative, that thing is stable. Once again, you can get it by the arrows, or you can just differentiate this function, and if it is negative, it's stable. Okay, so it's stable over there. If a is positive, it's unstable. Okay, if a is 0, then we have our Hopf bifurcation point. So this is exactly what we looked at in the previous example, because we're only analyzing the fixed point at 0, and this extra term has made no difference to it whatsoever. Okay, so for all practical purposes, you have a stable fixed point that goes unstable at a certain number, and what makes it a Hopf bifurcation, remember, you've got to find the limit cycle. Okay, you've got to find the limit cycle it goes unstable to. And so you can, by looking at the other places where the radius, in this example, where the other places where the radius does not increase. So r dot is also equals to 0 if this thing is equals to 0. Okay? And you should, when you get this type of problem, you should already recognize this. You've seen this before. It's the gradient of the double potential well. Okay? So it's reasonable to anticipate that if you want to have the limit cycle, you already have a guess for what the bifurcation diagram is going to look like. And if you wanted to plot the whole thing easily and quickly, you would see you simply have to plot A equals to r to the 4 minus r squared. Okay, that would give you the bifurcation diagram, the full one on here, and you could do that, so you'd simply be doing something like that. But since r is positive, it's just the one above the line. So you already know what the bifurcation diagram is going to look like. What you're going to do next is, I tend to push it analytically as far as I can. Okay, so there the amplitude is constant, and the constant amplitude has this value. And the reason I write it this way is because it helps me identify for what parameters I actually can find the value. Okay, so have a look at this. The first square root that gives me a reason for pause is over here. That's always got to be positive. So a, for this root to exist, a is always got to be greater than a quarter. Sorry, greater than minus a quarter. But another thing is, this whole thing, if I actually had to find the r star value, has always got to be positive. And here's a minus sign, so something this can be sometimes this thing can be negative, and I must find out where that is as well. So, and in fact, this thing goes negative the moment a gets too big. Okay, in the moment a gets bigger than 0, you're going to have 1 minus a number that's bigger than 1, so it's going to be negative. So then this second root disappears. Okay, so from this algebraic equation, I immediately know what values of a I can look at, okay, and should look at. You could have done it quicker if you looked at this thing. You simply plotted it, and in order to plot this, you had to look at all the zeros of A and the turning points, and you would get exactly the same result. Okay, you would find that the turning points occur at A equals to a quarter and R equals to 1 over the square root 2, and that the intercepts with the A equals to 0 axis occur at 0 and 1. So it's just two ways of doing the same thing. Okay, but let's go on, let's plot it. So we know for two roots to exist at least, this whole thing, both plus and minus, has to be negative, so it has to be less than 0. And the square root has to be positive, so A has got to be greater than a quarter. So we're going to basically play in this regime over here. And so the moment we've done that, we can say there exists two circular limit cycles at radius r equals to plus minus. We have just taken the square root of this thing over there. Okay, so the two limit cycles are there, and I now want to plot them. So the way I plot them is the first thing is if a is equals to a minus a quarter, there's in fact actually just one, right? Because r plus and minus coincide. So I put that point in. Okay, so if a is equals to minus a quarter, then r is equals to 1 over the square root of 2. And you can see that because the thing in the square root is 0, and you just have 1 over the square root of 2. So I put that point in. So that's the turning point for where the two roots split. Okay. Now the other thing I can note that if a is equals to 0, either r is going to be equals to 1 plus 1, so it's going to be equals to 1. Sorry, 1 plus 1 over 2 square root is going to be equals to 1. Or it's going to be equals to 1 minus 1, so it's going to be equals to 0. Okay, so the first branch is this one that goes from 0 all the way up to over there to a quarter, and it's this r minus branch, which I'm going to put in there. And the second branch is the one that's going to hit the axis at 1, and it's the r plus branch. Okay. And so once a gets bigger than that, bigger than 0, you only have the r plus branch left. Okay, and so I can let this thing continue out. Okay, and once again, I could have equivalently plotted this whole thing simply by noting from this condition that a is equals to this graph, and many people would have found this more intuitive and then simply plotted it like that. Okay, the region the algebra is useful is it gives you another way of finding the turning points and the fixed points and the intercepts. Okay, so you can now take this, you can work out the derivative of f on the fixed points, and you can find that this thing is, the top branch is stable, and this orange branch is unstable, and you once again have the stable fixed point. Or what you can also do is fill in the arrows. Okay, so you would simply take a point over here for a given a, work out what r dot is and put it in, and you would work out what r dot was, say, for a point over there, say at minus 2, and for a given, for a equals to minus 2, and for a given r, and you would just put it in there, and the arrows you would get would look like this. Okay, the moment you go above the limit cycle, this thing, the r increases in this region until eventually it hits there, where r dot is 0 again, and the same thing is true over here. So r increases until it hits there, and then above it, you have the things pointing down. So you can now see what happens if you start, say you start over in this region here, okay? There, r dot will always decrease. Okay, so if a is less than a quarter, your r dot is always going to decrease. Okay, so that whole region, and what you're going to have is basically a stable spiral. Okay, so that entire region is a stable spiral. If you now are in this region over here between a quarter and 0, what's going to happen is you're going to have your stable spiral over there, and you're going to surround it with that orange limit cycle. So that's your phase diagram. And remember, your Hopf bifurcation is basically occurring over here, where this limit cycle tends to shrink to 0 and eventually disappear. Okay? And the moment it does that, you see the solution disappears, and then it's going to come out here, but it's going to jump. It's basically going to sit here, and it's going to be taken all the way up to the next stable branch. And over here, between a quarter and 0, or minus a quarter and 0, you have this case where you actually have two possible basins of attraction, right? You can either go to the fixed point, or you can go to the stable branch over here. And the thing that separates the two basins of attraction is this unstable limit cycle. Okay, so above the unstable limit cycle, its r increases again, so you have an unstable spiral going in that region. over there, until you eventually hit the bigger limit cycle. Okay, so this is our stable limit cycle over here. The moment you're above the stable limit cycle, your R dot eventually decreases and they spiral towards the limit cycle. So everything will either go to one of these two things. So it'll either go to the zero fixed point. The basin of attraction to the zero fixed point is this sort of magenta color. The basin of attraction to this, the other alternative is a limit cycle with a radius of R plus. The basin of attraction for that thing is this kind of lighter violet area. Okay. And so this picture, you can see that these two limit cycles were pretty close together. So this picture was sort of drawn over there, right? If I now increase A further, but still keep it less than 0, our unstable limit cycle is going to shrink. And what the phase diagram is going to do is, once again, you have your small little stable spiral. It's surrounded by a limit cycle over there, which is now much smaller. In between it, you have this big region where it appears to be unstable. In some sense, the thing grows. Okay, so it spirals out till eventually you get to that point over there where you have your stable limit cycle appearing. And then above that, you again are attracted to the stable limit cycle. Okay. And now what has happened is the fortunate thing when your limit cycle, because of this term that damps it out, the minus r to the 5 term, what has happened over here is that if you increase A positive, all you have in this region, wherever you start, you have an unstable spiral. So it's going to spiral out, and it's going to hit the stable limit cycle over there. Okay, and then it's going to go again. And then you're going to have everything attracting to it. Okay, so this is an example where you have a subcritical Hopf bifurcation which goes unstable, but it is not so dangerous because you know you've designed your system to know exactly where it's going to stop. Okay, so that's a good system to design. What's also interesting is, remember when we did this example, or just this example in the one dimension, we said it would have hysteresis. Okay, so anything with two possible stable fixed points has hysteresis. So this thing actually also has hysteresis. So you can imagine if you were to start anywhere here, say with A very negative, it would always go to 0. Then as you increase A, you have the state where you'll stay on 0, except if something kicks you really, really hard, that you jump up to that region, and then you'll stay on this top branch. Okay, but for the most part, if you slowly increase A, you go here until the fixed point loses its stability totally. The moment A gets a little bit positive, you're immediately going to go up here. Okay, and you're going to stay on a limit cycle, so you're going to be oscillating. And if you then decrease A or decrease the thing, you're going to stay in that limit cycle until you eventually get here and you're going to hop down. So you once again have this irreversible behavior with A. Now imagine you have a guy that's flatlined, his heart's not beating. Okay? And what they do is he's sort of in this alive and dead state, right? So his heart is there, but he's still not completely dead, so he has the potential to actually have a beating heart, which is just a limit cycle. So when they shock him like that, they're basically taking his heart and shocking it into another region of phase space, and then they hope that when they've stopped shocking him, the thing is going to come down and it's going to find its stable region again and start beating on the limit cycle that actually gives life and pumps. Okay, so there's a very intuitive way of using these things to actually understand a lot of physical environment, or sort of physical things. So here also, if the Chernobyl reactor had been designed with a proper safety catch, even if it went a little bit unstable, if the design was fine, it could have hit another cycle which they could have controlled, but it wasn't. Okay. Huh? It's a very bad design to do that to nuclear reactors. In fact, nobody does it anymore because of what happened. I mean, the Chinese, and then there's always a risk, right? You know the Fukushima reactor that exploded, right? That reactor was well designed. I mean, the Japanese are really good at designing stuff. But every time you try and put in the safety catches, it costs money. So they had certain design parameters, like it had to withstand so many earthquakes because they have a lot of earthquakes there. It had to withstand tidal waves, and it had actually met all its parameters and more. It was over-designed, but it couldn't withstand the earthquake and the tsunami and the combination of salt water going into the reactor and actually helping it explode. You know, because it slowed down. So there's always a safety region that you go for. You over-design the thing, especially, and the more money you have, the more over you design it. But there's always risk, right? That something unexpected can happen. So yeah, that's that story. What is interesting over here, a last thing, is this is also a bifurcation point. I might talk about it a little bit later, but this is the bifurcation point. They call it a saddle node bifurcation point of cycles. Because what's happening here is you basically have this situation, and then you have that over here at a quarter, you have both unstable and a stable limit cycle, so it's sort of semi-stable being born together, and then they drift apart, giving rise to the stable branch and the unstable branch. So in some sense, it's a saddle node bifurcation, but it's not of fixed points, it's of cycles. You have two different cycles, a stable one and an unstable one born. And then the unstable one becomes the one that separates the two basins of attraction, and the stable one becomes the other basin of attraction. Okay, so this, in fact, is like the next kind. We've been looking at bifurcations in 2D first of just how fixed points change, their stability, their position, and their basins of attraction. And now we've looked at how fixed points become limit cycles and limit cycles become fixed points. And this is an example of how limit cycles are being created. Okay. Just another comment looking at this picture. What is the frequency of the limit cycle if this thing goes unstable? Nice exam question. Right, so look, when this thing goes unstable, it jumps to over here where R is equals to 1. Right, so it's going around with a certain frequency. What is that frequency? You've got an equation we haven't used. That's the trick. And it is this equation that you haven't used. Yeah, the angular frequency, not the full frequency. The angular frequency is 1 plus b, right? Because the angular frequency occurs at r squared. And r, in this case, is 1. So over here, it's 1 plus b. What will the frequency be before you jump from your limit cycle to the stable fixed point? Before you jump down. When suppose now you decrease the parameter a back to negative infinity, at some point there at a quarter you're going to jump. You're no longer going to be able to sustain a limit cycle. Yeah. Okay. So, and that's why when we looked at the examples so carefully, or the bridge examples, why they were measuring the frequency every time they looked at the bridges collapsing or they saw the oscillations, because it gives you clues as to what's happening in your system. It's the only clue you can measure. So frequencies are really, really important. And so you can actually see, that's why sort of with your heart rate as well, right? There's a range of frequencies when people take your heart rate. There's a range of frequencies that are optimal, there's a range of frequencies that are normal for a normal heart, and then there are a range of frequencies that tell you when you're in danger. And you have diagrams like this as well of where the heart is stable, what frequencies it has. That's all from me. Thank you very much. Questions? Complaints? Have a good vacation.